Hello, my talk will be about leveraging LLM reasoning with dual horn programs. A few words about why this is interesting. Well, let's start with the fact that negation as failure cannot provide bindings. It can filter existing bindings provided by other goals that generate them, but they cannot provide them. So that's definitely a limitation. We would want something that can positively state reasons why something is not provable, which negation as failure cannot do. So for that reason, we will revisit dual horn clause programs that deal constructively with negative information. This is motivated by the fact that there is an abundance of positive or negative facts that could be generated when LLMs are convinced to explore recursively a given fact that we would like to see what consequences it has, and that would lead us to dual horn logic programs. We want to ensure that reasoning is constructive, and this will happen with the combined horn clause and dual horn programs. And there are, of course, applications, in particular applications that take advantage of LLM-generated logic programs, providing a very interesting combination of backward reasoning, goal-oriented backward reasoning, and also goal-oriented forward reasoning. So let's start with this strong statement that negation as failure is considered harmful, a rephrase of Dijkstra's statement about go-tos at the time. Well, there is an interesting anecdotic mismatch here. The cat has been systematically vilified as procedural, non-declarative, and at the same time, negation as failure, which is in fact a two-liner expressed in terms of cat, has been glorified and also fine-tuned and refined in various ways in hundreds of very nice otherwise papers, and had an impact on developing new fields, in fact, in particular answer set programming. Now, beyond the anecdotic, let's look at the facts. Negation as failure tacitly elevates failure of a meta-level proof procedure into a construct of the object language. Negation as failure cannot explain, as no bindings of variables are provided. And while it is a shortcut that's very useful in programming, like not member of a given finite set would be an example, it conflates key concepts of truth and probability. And that's not a good thing for knowledge representation. So let's make a few steps toward constructive logic programming now. Well, horn clause resolution with a clause expressed in implicational form is intuitionistic valid. It's not the typical presentation of resolution, but it can be very easily morphed into an implicational form where inferences instead of having positives and negatives cancelling, would just propagate along implication lines. So negation as failure relies on a fallacy that true P implies provable P. This is the questionable part. Otherwise, by modus tollens, we have that, not provable P means not true P. And the combination of those actually gives us something that we know since Gödel, that there are unprovable true statements in any interesting language or theory. Intuitionistically, falsehood needs to be proven constructively by deriving an actual contradiction and without reliance on P or not P as an axiom, as it happens in classical logic. So this leads to our challenges expressed here as two open questions. Can we do logic programming while staying in a constructive, intuitionistically sound framework? And then, can we benefit from the knowledge encapsulated in the LLM's parametric memory while staying in this framework? So let's look at our answer to these challenges. Dual horn clauses. They have been discovered a long time ago as part of Schaeffer's dichotomy between P-complete and NP-complete subsets of propositional logic, among other things. But let's compare them directly with definite horn clauses here. So the disjunction-based notation tells that there is a positive one, that's the head of the clause, and several negative ones. Implicationally, that means, as we know from prologue, the head is implied by the conjunction of the literals in the body. Definite dual horn clauses will now, in disjunction form, will have one negative clause head and several disjunctively related positive ones, which also means, if we rewrite it implicationally, that the head here implies a disjunction of the literals in the body. So we look at the implication arrows here and here, and we look at the conjunction here, dualized as disjunction there. Of course, we have also integrity constraints, and integrity constraints, the most well-known ones tell that those propositions cannot be true at the same time. They would imply false. And that's the disjunctive form. And then for dual horn, it means that this disjunction here must be true, therefore at least one of them needs to be true. While here, we say that they cannot be all true here. In particular, when there are two of them, that's a form of weak negation, saying that P1 and P2 contradict each other and would imply false if we put them together, without bringing in that one of them needs to be necessarily true, as it happens in classical logic. So these are the interesting relations between those implicational and disjunctive expressed forms. The implicationals are weaker in intuitionistic logic, but they are equivalent in classical logic, so they collapse in classical logic. However, we prefer the semantic of the implication as we have it in horn clause logic, and that means that actually in intuitionistic logic we are dealing with a weaker inferential system, which is a good thing. The fewer things you assume and the more you can prove out of them, the better it is. Dual horn clauses then bring us to falsification as the key objective that we want, but done constructively. So dual horn clause is a disjunction of literals with at most one negative literal, or exactly one if it's a definite one. Same thing for dual horn clause programs, being a conjunction of dual horn clauses. We have a prologue-like syntax here, and we represent implication arrow with prologue syntax with this double arrow here, and we represent disjunction as the prologue way of doing it. A negated fact would become S implies false, corresponding to true implies S, or S if true, as we know from definite horn clause programs in prologue. So this is a small example of a dual horn clause program. Implications, P implies Q or R, and so on. Now, what we can do with this in a goal-oriented fashion is that we can falsify it by backpropagating falsehood from its consequences. So let's do it for P here. So for P, if P happens to be true, then Q or R is true. It means one of them needs to be true. Well, let's follow that Q would be true. For Q to be true, one of R or S needs to be true. Now, we know for sure that R is false. This makes this deleted here. So we still have S being possibly true, but S we know is false. Therefore, Q cannot be true. We get back here, it cannot be true. And R, we have seen that it cannot be true. Therefore, P cannot be true. We falsified P because its consequences brought us to falsehood. And that's how falsity backpropagates, very much like truth backpropagates from facts when we hit them in SLD resolution working on a prologue. So let's look at a typical use case. So the objective of dual horn programs is to describe constructively why something is not true. Therefore, we want to falsify the initiator goal by backpropagating, as we have seen, from its negative, in a more general sense, undesirable, unwanted, harmful, impossible, and so on, consequences. So we see here an instance of goal-directed forward reasoning. What we have as a nice property is a polynomial complexity for the propositional case that's found in Scheffer's dichotomy theorem. So it's a P-complete class, very much like horn clauses. And the nice thing about that is that because LLM generated programs that could be very large, LLMs know a lot about the world, will be propositional. Therefore, we don't have a problem computing a fixed point with a fixed points computation, their minimal model in basically linear time. This brings us to our embedded language into Prolog. Symmetric logic programming, SymLP. It combines horn clauses and dual horn clauses into Prolog. Now we have a bit of syntax here. We mark with plus facts that are true and with minus that are false. That's a shorthand. And then we use this to represent implication, and this to represent reverse implication. So minus p is a shortcut to p implies false, and plus p is a shortcut to true implies p. So we borrow from Prolog the usual notation for conjunction and disjunction, and that's the syntax. Now we have a compilation scheme. Let's look at this clause here in dual horn form. So P0 implies a disjunction. Well, we have kind of seen that we solve it by falsifying its consequences. So the idea is that if we turn it into a horn clause by saying we turn this into P0 if P1 and Pn, so the dual actually, and we place the result of all those compiled forms into a module false, then we know that if this succeed in the module false and produce bindings, if we have variables, which we could, then they would express what cannot be true constructively. So a successful proof in this module false then implements successful falsification of the original dual horn clause. And this compilation ensures that backward reasoning on horn clauses mirrors forward reasoning on dual horn clauses, and it preserves efficiency and logical correctness. So now let's look at a first example. Well, this could be politically relevant in the upcoming month in US. Losing the Fed's independence. What would be the consequences of that? And we'll explore that at multiple levels of recursion. So at first level, one of the things that come out here is increased political influence on monetary policy, with consequences, among them not very good ones: short-term economic manipulation, eroded investor confidence, heightened market volatility, policy-driven inflation risks, and then we can explore eroded investor confidence further down, and some of the negative consequences more concretely come out as we do that exploration level by level. So if all those things turn out not to be a good idea, we could hopefully convince a decision maker that losing the Fed's independence is not a good idea. So the machine that handles this recursive unfolding to extract from the LLM's gigantic parametric memory very specific knowledge centered on a given topic or statement is this deep LLM application. It's available as a Streamlit app, and in the paper there are multiple links to code. So it works by on the positive Hoare subset by doing SLD resolutions, close selections via unification, but this is actually replaced by an LLM-driven dynamic close head creation with an option of focusing by proximity of embeddings to ground truth facts. So it's a multi-agent system actually, kind of ahead of today's emphasis on agentic systems. It's about a year and a half old. The deep LLM has been described in more detail in several previous papers that are cited in the paper. Now, because our dialogue units are sentences, the logic is propositional, we have a client-side management of the LLM's memory, and we work with the equivalent of a goal stack and a goal trace, recording our steps on the current search path. Instead of variable bindings, when we work in the propositional domain, answers would be traces of justification steps, clearly explaining where they are derived from. And then, when depth limit is reached, the items on the goal stack can be treated as abducible statements that can be hypothetically assumed and then checked against integrity constraints. In particular, they can be checked by seeing their consequences in a dual horn program. If the consequences lead to unpleasant facts, negative facts, then we will interpret them as failing. Otherwise, we will interpret them as positive abducibles. They could still be filtered out by integrity constraints once assumed. So exploring a topic with deep LLM, we have a choice of topics here, in particular for dual horn programs. We are interested in consequence predictions, and here we choose abducible clauses in the open world semantics for horn clause programs. That's a relatively complex and focused and narrow concept in a way, and we can see here how it reduces to several more refined concepts that we could then describe as a logic program, as we see it here with disjunctions and conjunctions in it. So that's basically what deep LLM does for us. And now let's look at some applications of programs that could be either handmade, like I did this one, or generated by an LLM. So this is default reasoning dual view. Usually to compile and execute, we include compile clauses.pro. The compiler works as a term expansion mechanism, so it's very little bureaucracy with it, like compiling to a file, then loading it. That's not happening. It's just expanding the dual horn clauses into corresponding horn clauses in the module false. So a bird can fly, and for that it should not be a challenge bird, which means that if we have that eagle joy is not a challenge bird and humming Jenny is not a challenge bird, then they would fly. In fact, we don't even need to say bird here. It's enough to say that they're not challenge bird in the module false, and then we accept that they fly. That's kind of more direct than the corresponding famous default negation-based interpretation of the same Tweety problem. Let's look at something a little bit more interesting, how we combine positive and negative advice in a SymLP program. So this is about a little stock market advice, about a cautious, kind of conservative-ish buy. Something needs to be recommended and also safe. So things that are safe are if they are in the false module volatile, so if they're not volatile, if they're not overvalued, and if it's true that they are stable. So you see the module true where the horn clauses go, and the module false where the dual horn clauses go. So we have a series of facts here about some of the stocks. I didn't use the tickers, I just expanded them so people might recognize what they are. And we have here what volatile means as an implication, big price changes in the last month, and then we see who didn't have big changes in the last month, and who's not overvalued. And based on that, we can now run it, and we see in the module true, we call cautious buy, and we get the answers for QQ, Apple, Meta, and Berkshire, which are a subset of the things that got recommended here. So after combining positive and negative facts and inferences drawn in the Horn module true and the dual Horn module false, the call to cautious buy in module true will generate the answers that I just showed. So what are the merits of this? Well, integration of positive and negative advice for practical reasoning, evaluating stocks for cautious investment in this case, rules combine negative warnings like volatility and positive assurances like stability. It facilitates a nuanced and data-driven decision-making process, and of course it shows the utilities of Horn closed logic in a real-world context. So let's look now at some of the other deep LLM generated Horn and dual Horn programs. They generate propositional logic programs. We have goal-driven backward reasoning in Horn clauses that decomposes complex tasks into disjunctions and conjunctions of simpler tasks. And then we have forward reasoning that dually help explore consequences of hypotheses with the purpose of being eventually falsified. So the deep LLM system recursively explores a topic of a given depth, and it's, as I said, an agentic system with interactors to manage the LLM interaction task, recursors to handle iterative subtasks, and then the refiners that enhance clarity and verify reasoning steps. In particular, they could veto some of the conclusions here. So they are basically critical agents that filter the enthusiasm of the recursors otherwise. Logic programs generated are explainable and modular, and then as a practical consequence is that deep LLM can minimize inaccuracies and biases in LLM outputs. So here's another one related to escalation risks after use of tactical nuclear weapons, and that could lead to a global nuclear war or uncontrollable retaliation steps. This is explored deeply with a lot of consequences, and then hopefully again a decision maker would refrain from proceeding with something like that, knowing how bad the consequences are. So now let me finalize before we get to the end. Dual Horn programs versus constructive negation. So while dual Horn programs produce bindings of the form x equal t, with t a term, a ground term usually, constructive negation reduce a negated goal to bindings of the form x different from t. So they tell what x cannot be, information only useful if a generator provides candidates for what x could be, and they are usually part of a constraint solver where that's happening, and then they help, of course, making the constraint solver more efficient. But what we discovered or recovered here is a genuinely constructive mechanism to deal with inference about negative facts without tacitly reflecting the failure of the proof procedure at object language level, as in the case of negation as failure and its constructive elaborations. So the conclusion would be that we bring in dual Horn clauses that have syntactic simplicity, have a straightforward semantics. We have a compilation scheme for them, and in SymLP, this embedded language, Horn and dual Horn programs combine fully constructive intuitionistically valid reasoning about the two sides of a decision process. Using the deep LLM system, we can generate goal-oriented backward and forward reasoning propositional programs. And for very large LLMs generated programs, we have actually a linear algorithm to find the unique minimal model, because we stay in the p-complete realm. So we believe that our effort has revealed a novel form of synergy between generative AI systems and the logic programming tools. Thank you.